Okay, so back to constraint optimizations, was what we were talking about before. Again, the big idea, our motivation for this was, how do we deal with sets that have boundaries? How do we deal with the boundaries specifically, right? And so we made the observation that, well, you could describe, in this context, we will describe boundaries with equations, aka constraint equations, right? And once you make that observation, that's like, well, all boundaries that we're going to consider here are represented with equations, but not every equation is a boundary. So the technique we're about to explore here applies even more broadly than just those kinds of boundaries. Okay. All right. Where's my little eraser? Here it is. Okay. Right. So a little bit of terminology about this and that. Be careful with the terminology. We made the observation that the constraint gradient is always orthogonal to the constraint set. Right, that's a neat geometric observation. We next observed that, thinking about, again, same constraint set, the objective gradient also tells us a tremendous amount of information. If it's not, well, let me not go to the failures. If it's pointing like I've got it drawn in the picture here, I know for sure, 100%, there is no way that this point could be the maximizer. Right? How could it be? That can't be the maximizer. After all, as I move along this path, and therefore at that moment have that velocity, this dot product, computing the directional derivative, is positive. Well, that means the function's in the process of increasing. And again, this is this sort of simple-minded, very low level of sophistication ruling out argument that we've used in those previous contexts, starting to do optimization. We eliminate points as possibilities with this really simple observation, and it rules out the vast majority of the points that we're worried about. So it's super powerful, even though it's pretty simple. Okay. All right. So as drawn in this picture, that point that we have in blue here, this point could not possibly be where the maximum of this function is achieved. Okay. Right. So how could this argument fail? Well, the reason we're interested in why this argument might fail is because it is where this argument fails that we don't know what's going on. That's therefore where there might actually be a maximizer. And therefore we have to admit that we can't rule it out, and we have to, we have this little cheap workaround where we call it a critical point to make it sound like we've actually drawn a conclusion. The reality is that critical point means we have no idea what's going on. Right? So where does this argument fail? Namely, where are our critical points? And several ways this could fail. We assume differentiability when we convert the directional derivative question, our ruling out process, to a dot product. That requires differentiability. If the function's not differentiable, forget this argument. You cannot eliminate that point. Such points have to be critical points. Here's another possibility. Let's suppose that instead of that, let's suppose that our objective gradient is also perpendicular. Well, then its projection, so notice the direction we went here was the projection down to the tangent plane. The projection would be the zero vector, which suggests that I'm dotting with zero, and therefore I don't get to conclude that my directional derivative is positive. So again, my argument fails if the objective gradient is perpendicular. And lastly, of course, if the objective gradient is itself the zero vector. Okay, so these are the ways that our argument can fail. Here, let me zoom in now. Any one of these things happens, we've got a critical point. Okay, now this is not what you're going to do work with. You're not actually going to, day in and day out check these conditions. The reason why is that this one is a little bit hard to deal with algebraically. It's just a practicality issue. How do you check if a vector is perpendicular to a set? This is hard to write down. Right? So what we're going to do instead is we're going to replace those conditions with these conditions. These are easier to work with. And I'm going to show you why this is just as good Much easier to work with and just as reliable. By the way, it looks like there's a typo. There's not. A lot of people look at this and say, okay, well, obviously this one's equivalent to that one, so that's clearly right. Perpendicular to constraint set. Now let's go back and talk about this. We know that our gradient of G is always perpendicular to the constraint set. I want to know when that vector is also perpendicular to the constraint set, and so there's a temptation to say, oh, well, gradient of f being perpendicular to the constraint set is simultaneous with it being a multiple of the gradient of G. And that's usually true, but it's just, we've got to be a little careful. I'm going to leave an asterisk on that, and we'll come back to it in a moment. But again, so a lot of people think that this is equivalent to that. And then the apparent typo comes when people say, oh, well, okay, well, this surely you meant f down here, right? Shouldn't that be f? Okay, so let me explain what's wrong with that reasoning. And by the way, keep in mind, we're looking for critical points. We need to make sure that we find all the critical points. We need to make sure that the algebra that we work with produces all of the critical points. So therefore, I need to know that every point satisfying one of these conditions must satisfy one or the other of these conditions. So that's why I'm going to go through this. I'm going to go through and check one at a time. If a point satisfies this condition, which one or several of these conditions must it satisfy? So this one, obviously, has to satisfy that one. That's the easy one. Okay. This one is the tricky one. Let me come back to it. This one, which of these three conditions does this have to satisfy? And this is a sneaky one, but it has to satisfy this one. If a point has the feature that the gradient of f is equal to 0, I guarantee that it is a scalar multiple of the gradient of G. That scalar is 0. Right? So that's another easy one. Right? So the tricky one is, what happens if the gradient of f is perpendicular to the constraint set? Which of these conditions does that have to satisfy? And it could be either of these is the thing. There's this little subtlety to it. And let me explain with a picture. If the gradient of f is perpendicular to the constraint set, here are the two possible pictures. It is possible that by being perpendicular to the constraint set, yes, it is a multiple of the gradient of G. But it is also possible that the gradient of f could be perpendicular to the constraint set and not a multiple of the gradient of G, because the gradient of G could be 0. And I don't care what scalar you multiply by. The gradient, if you have the 0 vector, there is nothing you can multiply it by to get a non-zero vector. Right, so the point is, again, the sort of the simple-minded, that's the asterisk from back here. This picture assumed inappropriately the gradient of G must be non-zero. Of course not. No, it could be all. Who knows? There's no rules there. So points satisfying 2' have to satisfy one or the other of these, but we don't know which. Okay. All right, so there's this weird little thing. Again, this looks like a typo, but it's not. Okay, so what we are going to work with day in and day out are these conditions right here. So this is you can write this as a theorem. I'm just going to call it the method of Lagrange multipliers. And the way you're going to find critical points on boundaries, or more broadly, the way you're going to find critical points on constraint sets, is by looking for points where the function fails to be differentiable. Any such point is a critical point. You're going to look for points where this algebra is satisfied. Any such point, critical point. And you're going to look for where this happens. Now, just a little semantics, just so you'll know what I'm talking about going forward. I give names to these conditions. This is the differentiability condition. I think that's a pretty clear name. This we call the Lagrange condition, or I call it the Lagrange condition. This is the one where, to be totally honest, most of the time, that's where you're going to find the critical points that actually are the maximum. That it's the one that works usually. I cannot emphasize enough. You can't just write that one condition down and take your chance, fingers crossed, that that'll give you the critical point that you're looking for. That's not okay. I emphasize. I know I say this a lot. I think this is appropriate, but this is not a class about answers. It's a class about reasoning. And if you don't check all the possibilities, then your reasoning is simply not valid. Right? So anyway, that said, I think it's reasonable to call that the Lagrange condition. This one, for reasons that are way beyond the scope of this course, is usually called the degeneracy condition. And it has to do with the fact that when there's a certain type of way in which an equation describing a surface, the solution set can look really bad in ways, again, that we can't go off into, as is very often tipped off by this condition. So it comes from another context. But anyway, degeneracy was how we describe that. Okay, so there's our tools. Here's an example. Suppose I want to find all the critical points of this function right here on this plane. Now, I remind you, this function does not have a maximum value in general. That function could be really, really big or even bigger. Right? There's no upper limit how big that function can be. There is a limit on how small it can be. It certainly can't be smaller than 0. But neither of those is the question we're interested in. We want to know, on this plane, what are the critical points? And that's a harder problem. Right? Now, it can still be as big as you want. Right? Make x a billion. Make z like negative a third of a billion, or what? Balance it out, right? But you get some enormous numbers that are going to make f huge, right? So so this function can still be as big as it wants, but on this plane, this cannot be 0. There's no way on that plane that you can make f 0 anymore. So since it can't achieve its sort of theoretical algebraic minimum, what is the actual achievable minimum? Right? And there's lots of applications to problems like this. Just a quick side note before we get into the algebra. Maybe this constraint represents, you're running a business, and look, you've only got so much money, and you've only got so many employees, and you've only got so much other constraints to what you can do, and you can spend more money on materials, but then you can't spend as much money on employees, and all these various things that have to balance out. So this may be the ways in which you, as a mortal, have your hands tied in your situation, and tied though your hands are, you still want to, under those circumstances, make as much money as possible, or take as little risk as possible, or have as high efficiency of your whatever. Right? You still want to maximize some goal. Okay. Okay. So let's go through the steps. We got 3 conditions to check. Take them one at a time. Our function f, does it fail the differentiability condition anywhere? Is there any point where this function fails to be differentiable? No. It's a polynomial. All polynomials are differentiable everywhere. So now, sometimes I like to call this good news. Right? We tend to think of differentiability as being a good thing, not a bad thing. So it's kind of good news, but it's also kind of bad news, because it has given us now no candidates to check in our search for a maximum. So you can argue with yourself as to whether this is good news or bad news, but certainly we have no critical points resulting from that condition. Okay, next, the degeneracy condition. Our constraint function, recall, the constraint function is a function for which a level set gives you the constraint, the constraint equation. Our constraint function, we need to know when is its gradient equal to 0. Well, never. Good news, bad news. But there are no values of x, y, and z that will make this equal to 0. Yeah, sometimes it's real easy. All right, so We're kind of over 2. We have no critical points yet. So we move on to the third condition, the Lagrange condition. Here it is, Lagrange condition. We've already computed the 2 gradients that we need. Well, up here they are anyway. So there's our objective gradient, and there are its coordinates. Here is your constraint gradient. There's its coordinates. And this equation, this Lagrange equation, if you break it out one coordinate at a time, gives you, therefore, these 3 equations. And we need to know where might this happen. And so now we've got a little bit of a problem. We've got a system of equations, and that's work. It's effort to solve. Everybody on board so far? Everybody see how I checked all 3 conditions? I cannot emphasize that enough. By the way, just strategically speaking, on the exam, I don't want to undersell this point. But again, it's about your reasoning, right? And so you do have to check, even if look at what happened in this case. We checked these 2 conditions and got no critical points, right? It didn't checking these 2 conditions did not contribute to us finding the point that we're looking for. The point is, if you don't check these conditions, your argument is invalid. Right? You have to check all possibilities before you claim you have all the answers. Okay, so make sure to, so on exams, this will be worth points, right? We only have 1 exam remaining, of course, the final exam. But on the final exam, if you don't check your differentiability condition, expect to be docked points, because, again, legitimacy of the reasoning. And likewise, if you don't check your degeneracy condition, independent of how obvious it is, you're gonna lose points. And again, this one tends to be a big one. So look how easy it is, by the way. So easy. All you have to do is say, yep, not 0. And you just saved yourself several, quite a few, as many as 5 possibly points on the exam. Okay, so back to the Lagrange condition. We have these 3 equations, and let me remind you of something. We are looking for critical points on this set, right? We are only allowed ever to be on this set. I couldn't care less about what may or may not be of interest on this f function outside of this set. And so this equation, this constraint equation, is actually a 4th equation. Critical points only matter, they're only even defined, they only even make sense if they're part of the set we're constrained to anyway. Right? So when we write down these equations, it's important, don't just write down just the Lagrange equations. You have to also add in the constraint equation as well. Because if you find some point out in the middle of nowhere that satisfies these conditions, it doesn't matter. It's not a critical point. If you label it as a critical point, it doesn't look good, right? So, yeah. All right. So here we have 4 equations, 4 unknowns, and these can be hard algebra problems. Generically, nonlinear systems of equations are extremely difficult. Another aside, that makes it challenging for instructors to write good constraint optimization questions. Because, again, we have to make questions that test your ability to actually do what we want you to be able to do. We can't make questions that are not tractable. That's not fair or reasonable. We're not going to do that. We're not monsters, as I like to say. So it's a little bit of a tricky challenge to make a question where the algebra is doable, but not just falling down trivial. Right? Anyway, like I said, it's a bit of an aside. Okay, so what do you do? There is no single method that will always work. I'm going to show you what very often works. All exceptions granted. A good first thing to try. You remember how I always say, if you're going to parameterize something, first thing to try, graph parameterization. Right? It works super often. Right? So likewise, first thing to try in one of these situations, solve for lambda. You got 3 different ways to solve for lambda. Write down all of them, right? These first 3 equations tell us that lambda has to equal to all 3 of these things. Right? Write that down. And the neat fact is, well, if all 3 of these things have to equal to lambda, then they also have to all equal to each other. And now I've got some more equations to work with. Very often, so this is called eliminating the variable. Right? Very often this will get you to what you need, and that's the foot in the door here. So these equations, I can then plug into there. Oh, well, let me do it like this. Rewrite everything in terms of x, plug it into there, and now you've got, instead of an equation of 3 variables, we've now turned that into an equation of 1 variable. And when you have an equation of 1 variable, it's super easy to solve. Right? So now we know x is 6. And once you know x is 6, then I know y, and I know z. Right? So that's you pull on that one string and the whole thing unravels, roughly speaking. It works out really nicely. Very often this will work. Let me pause for questions. Does everybody follow the algebra? Everybody see the strategy? Everybody see how we applied all 3 of the conditions? Any of that? Okay. So we only get one critical point, and now I appeal to your geometric intuition. This point 632. On this plane, this is a critical point of the distance squared function, right? And what that is it's the point on the plane closest to the origin. Geometrically, I think that's pretty believable. Okay. Alrighty. So there's a million other examples, again, there's only so many, though, that are algebraically tractable. If you were to write down sort of a random, come up with some random polynomial f and make a random sort of polynomial constraint with constraint function g, right? Generate your own problem and say, well, whatever, it's just polynomials, and you start writing down the algebra and then you try to solve this system, you'll end up with a nonlinear system, and it's very often just not feasible to solve. So it's real tricky to come up with your own examples, but what you can, of course, do is go through all of my old midterm exams, all of which are online, and pretty much every problem that I've ever been able to think of has made it onto one of my midterm exams. So there's a lot of good old exam questions there. I encourage you to take a look. Okay. What if you have multiple constraints? I'm going to talk about this a little bit for a couple of reasons. First of all, I want you to know what the question looks like and the general sort of context. So suppose you have a constraint. And again, maybe you're an economist and you've got some constraint involving, look, I've only got so much cash, I can spend it on various different things, but I only have so much cash. So there's a constraint. But then maybe there's some other constraint that doesn't involve money, but you're constrained for other reasons that, maybe it's environmental regulations, let's just say, right? So you can buy so much of this raw material and you can use so much of this raw material, but the rule says that some combination of those, whatever the combination is, has to add up to no more than, a certain amount. So you are no longer looking at a single constraint problem. You have these 2 different constraints. You are stuck on the intersection of those 2 planes, surfaces. So what do? Right? How do you find the critical points? Well, there's a whole story. I'm not going to go through the whole story of how you get to the conditions. I'll tell you why momentarily, but this is the punchline. You have, again, a differentiability condition. You have, again, what I'm going to call a Lagrange condition. And I call your attention, just for pattern purposes, to the fact that it's like, we're just adding one extra term onto what had previously been our Lagrange condition. So it looks just like the single constraint condition. And then where things get a little weird, and there's a whole story, there are now 3 degeneracy conditions. You have to check all 3. Any point satisfying any one of these 3 degeneracy conditions is a critical point, and you have to check it too. Okay, so if in your futures you find yourself looking at a 2-constraint optimization problem, then here's how you do it. And the reason I say in your futures is because in Math 212, you're not responsible for this. We're not going to have any final exam questions that are on to constraint optimization. So the reason I showed you this, again, one of them is sort of, cultural or, sort of distant, preparation just in case you might need this someday. But also the algebra here of this example has a nice example of something that even in the single constraint case, you have to be on the lookout for. So here you'll notice we're trying to maximize a certain function. We have two constraints and thus two constraint functions to worry about. And you can go through all the conditions. I want to draw your attention to checking the G degeneracy condition. Let's check for where the gradient of G is 0. I mean, it's the same kind of thing you have to do with single constraint, so this is very relevant. Well, here's the thing. There's a temptation to talk about the entire z-axis. Because after all, anything that's on the z-axis makes this gradient of g equal to 0, and doesn't that make it a degeneracy? Doesn't that make it a degenerate critical point? So, not quite. Again, I remind you, we are not interested in random points off in the middle of nowhere outside of our domain. We are only interested in points that satisfy our two conditions. And notice that even though there's infinitely many points on the z-axis, not a one of them satisfies that constraint. All right, so heads up, be on the lookout for this. Not everything, so finding degenerate critical points, yeah, you write down this algebra, but don't forget you've got to always compare back to your constraints. And don't write down as critical points things that are, again, off in left field somewhere that don't have anything to do with the question. Doesn't look good. Okay, and then blah, 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 there's other things. The algebra on these can be horrendous. So if just for entertainment value, if you want to go through and see, here we have a 5-variable 5-equation system, and seeing how that works out can be quite rough. The lucky break here is that this equation tells us mu. Once you know mu, then you can eliminate lambda to get that. And once you know that x is equal to 2y, I plugged it in the wrong one. Once you know x is equal to 2y, then you can solve for y. Okay, so anyway. All right. Questions about this? Anybody have any questions about that degeneracy little hiccup there? Okay. All right. Last thing I want to show you. What global extrema. So now I'll remind you, we've been talking about critical points. How do we find critical points? How do we find points that we don't know what's going on? Right? It sounds like you're really doing something when you say we want to find these critical points. But again, that's just a label that we put on things where we don't know anything. So the more legitimate question is, I suppose it's interesting to see where critical points are. But look, I got to make a decision here. I run a factory. I got to decide how much of this material do I buy, how much of that material do I buy, and which one's going to give me the most profit, right? I don't care about this abstract discussion of, well, there are 3 critical points, right? How do I make money? Or I'm designing an engine. Which of these several scenarios is going to make my engine the most efficient? Right? So global extrema are the way we talk about that. Remember, we have this theorem here that says if your domain... Oh, excuse me. I got ahead of myself. If your function is continuous, and if your domain is closed and bounded, then yes, there is a global maximum somewhere. And by process of elimination, it's got to be one of the critical points. And therefore, you can conclude, again, if your exasperated factory manager can conclude, okay, well then this has got, checked all the critical points. This is the one where it makes profit the biggest, and so that's the one I should do. Okay. Okay. Just keep in mind, we've got one means for finding critical points in the interior, and we have another means for finding critical points on the boundary. And so just make sure to check both of them, right? You got to find critical points in both areas. So here's an example. And again, this example is good partly for mathematical reasons and partly as a heads up for the kind of algebra that you're going to bump into sometimes, right? So we want to find extrema of that function on this domain. Notice that this domain has an inequality there. So this is a solid ellipsoid. It has an interior, but it also has a boundary. I got to check for critical points on both. Okay, so the interior critical points. Take F. Compute the gradient, see where it's equal to 0, easily concluded that's the origin, and so I've got myself a critical point. That's easy, right? Straight up, plug and chug into the method. Let's talk about those boundary critical points. This is obviously differentiable. Hey, by the way, I really should have written that down. Shame on me for not writing that down. Here, look, this is what will happen on the exam, okay? I didn't check the differentiability condition, right? Shame on me. So, that said, the function is clearly differentiable, so no critical points there. Let's see here. Degeneracy. Here's our constraint gradient. If I set it equal to 0, that gives me this point. Again, don't move too quickly. Don't think, well, therefore that's a critical point. That's a degeneracy critical point. No, it isn't. Because it's not on the boundary. The boundary is the ellipsoid, the surface ellipsoid, where you have equals 36, and if x is equal to if x is the origin, then that's not there. So this does not produce any critical points. Now, of course, obviously, we've already agreed that that's a critical point for interior reasons, right? But anyway, don't label this as a degenerate critical point. And then the Lagrange condition. So here's your Lagrange equations, and now plus we also have to add in the constraint equation. It is very tempting here to argue as follows. Let me step on the landmine to show you where it is. This tells me very clearly, it seems, that lambda is equal to 1. But this tells me, seemingly just as clearly, that lambda is equal to a fourth. There is no way that lambda can simultaneously be both 1 and a fourth, and therefore there's no, so it seems, no Lagrange critical points. That's extremely tempting. We have all been trained inadvertently from a young age to do this little algebraic move called canceling, right? So it is tempting to just kind of knock off the x's and say, okay, well, knock off the 2's, and therefore lambda is equal to 1. And that is not valid. What if x is 0? You can't cancel zeros, right? Here's a true fact. This is absolutely true. You cannot cancel the zeros, right? Okay, so what we have to do then is we have a much harder algebra problem than it appears, and what you have to do is break it down into cases. There are, here's an exhaustive list of cases. Unless we're talking about the origin, we've already considered the origin, by the way, right? We already know that's a critical point, so we're not responsible for the origin anymore. Unless you're talking about the origin, at least one of these corresponding variables has to be non-zero. So these are highly overlapping cases, but nevertheless, if I consider all three of these cases, we're good. And check it out. If x is non-zero, at that point, I can conclude that lambda is equal to 1. if lambda is equal to 1, I can plug that into these two equations, and that tells me, right, if lambda is equal to 1, I've got 2y is equal to 8y. Clearly y is 0. Likewise, z is 0. And if y and z are 0, so if the algebra's, is, gotta be careful. Oh man, I'm gonna have to go all the way back up to here. If y and z are 0, and I'm on the boundary, then that means that x has got to be plus or minus 6. Right? So there's a couple of critical points that I would have missed if I'd not been careful. In fact, likewise for the other two cases that you have to consider. So in fact, grand total on the boundary, if you had been, a little too fast and loose with your cancellation and concluded that there were no boundary critical points, you would have missed 6 critical points, including the ones where the function is the biggest. You would run an inefficient factory. You would design a poor engine, right? If you weren't careful with that one little microscopic point of algebra. Okay, everybody happy? Any questions about the stuff here? Okay, all right. It's been fun, y'all. Have a good. Let's see, what do we got here? Reading period, and then extremely long wait until our final exam on Monday next, right? Yeah. 9. That's right. In the morning. That's right. 9 to noon. And see you then. Okay. Have a good one.